Hi, my name is Adolfo Campos, and today I will explain the experiment of the ideal gas law. So, the ideal gas law is the formula that it's in uh, right now, which says that pressure times volume is equal to the number of moles times a constant called R times the temperature. This is a formula that relates both pressure, volume, and temperature, and tells us how they change when one of the three are changed. This formula assumes some things, for example, that this is an ideal gas, so therefore the molecules in the gas do not interact with it. But in practice, they can roughly estimate how some gases work. So in this experiment, we're going to try to test how accurate this is and try to get results from the formula. So for the experiment, we're going to use the apparatus that's in there. It's a syringe. This range has markings for the volume in cubic centimeters, but more importantly, it has a thermistor right here, which can tell us the temperature inside of the syringe, as well as a pressure sensor, which is connected to this apparatus right here, which can tell us the absolute pressure of the system. All of these is connected to the Pasco interface, and so we can see in real time both the pressure and temperature of the system. So the experiment is divided in two parts. In the first part, we're going to use the syringe and make some movements in order to get different data points for different situations and graph them and see how they compare with the ideal gas law. And for the second for the second part, sorry, we're going to try to get the number of moles inside the gas using the data points we got and the ideal gas law. So here's the setup for the first experiment. As you can see here, we have the syringe. And what exactly we're going to do is first start at around 40 cubic centimeters. You can see here it's actually 42 cubic centimeters of volume. And then we're going to fastly make it go downwards, therefore reducing the volume. All this time, the both temperature and pressure are being recorded. So the volume gets around 22 cubic centimeters, and we're going to hold it there until the temperature reaches the ambient temperature again. So therefore, we need to wait some time in order for that to happen. And after that, after the temperature equalizes, we're going to let go of the syringe, and so it will start an upward motion again, slowly, due to the differences in pressure. We're also going to record how both pressure and temperature change right there. You can see how it's going upward. For the second setup for the experiment, for the second part, sorry, we're going to use those specific values for the volume. We're going to see how the temperature and pressure behave in those volumes. Exactly how we're going to do this is that, for example, first we're going to make this range go to 60 cubic centimeters, and we're going to record both pressure and temperature until they are constant. They do not change anymore. And then we're going to slowly go down to 55 cubic centimeters and do the same process, wait for both pressure and temperature to stabilize, and repeat that for all of the values. And after that, we're going to compare them in a graph and see how the slope can tell us how many moles there are in the gas. Okay, so for the results of the first experiment, here is the graph of temperature and absolute pressure over time. You can see clearly all the phases of the movements of the syringe. First, around this part, both pressure and temperature are at the ambient values because the experiment hasn't started. Then on these peaks right here is the quick motion downwards of the syringe. Then you can see the time it takes to stabilize. You can see that at the end both get roughly horizontal. And then we let go and the slow upwards motion happens. You can see both drop, uh, but after some time they stabilize again. Okay, so for the first part, we're going to try to compare two values using the ideal gas formula and see if they gives us accurate results. So for the two values we're going to choose is this first one of at around 5 seconds. We can see here values that are in order are time in seconds, the pressure in kilopascals, the temperature at centigrades, and the volume. This corresponds to a value around here, where both are at the ambient temperature and pressure. And the second value we're going to compare is to this one, which has the same quantities in the same order. So this will be around right here in time, on which the temperature has reached the ambient temperature again. So therefore, we can use the ideal gas formula, and now as in this case, both the moles, temperature, and R is a constant, therefore there is no change in pressure times volume. So therefore we can say that the initial pressure times volume is equal to the final pressure times volume. Using this, we can see how under the data how exactly they are, and as you can see they are a bit different. This because we haven't accounted for the volume that was already inside the syringe. This volume is called volume zero, and the correct formula in order to account for it is this one right here, on which it is summed to both the numerator and denominator of the volumes. If we then clear this formula for volume zero, we get the next formula, in which pressure 1 times volume 1 minus pressure 2 times volume 2, and all of that divided by pressure 2 minus pressure 1 gives us volume 0. So when we account for this, we get that volume 0 is around 2.3 cubic centimeters. Knowing this, we can try again and use another set of values. Here we have the graph again. For the first value, we're going to use the same first value we used on the previous try, which will be when both are at the ambient pressure and temperature. But now for the second value, we're going to use this one. This one corresponds to the peak in temperature, this point right here. This because theoretically they should be the same. They should follow the ideal gas law, no matter the temperature. And because the temperature after this point starts to go downward in order to reach ambient temperature, this is the most extreme point we have on which they should still follow the ideal gas law. Because after this, the temperature slowly decreases in order to get to the ambient temperature, not accounting for the ideal gas law. So here are the results. Here we have B10, which is volume 1 times, the initial volume plus volume 0, and volume 20, which is volume 2 plus volume 0. And here are pressure times volume over temperature for both parts. This is because the ideal gas law tells us that, because remember PV equals an RT, and as both N and R are constants, we can see that this time the amount that doesn't change is pressure times volume divided by temperature. So therefore, the two of them should be the same. But as you can see here, they are quite a bit different. Here we get 126 kilopascals times cubic centimeters over centigrades, and here we get 96 of the same unit. This is an error of 30, which counts to around 24% of error, assuming that the first value is the theoretical one, the more correct one. This discrepancy can be accounted by a lot of things. For example, as I said before, the temperature tries to always go back to the ambient temperature, so therefore it's always lower than it should be. And secondly, as you remember, this is the ideal gas law, and there is not an ideal gas. So therefore, some error is going to come in that because the molecules are interacting with each other. And third, it's maybe an error in our calculation, in our data, especially in volume, as it is not as exact as both pressure and temperature. So therefore, any small change in volume not only changes the initial and final volume, but also the correct amount for volume 0. So therefore, this is why, because it is the explanation of why the error is so high. but it's not extremely high. It is roughly an estimate. So therefore, the ideal gas law can somewhat be applied in this case. But this leaves us some question about why these values behave the way they did. First of all, they are both at ambient, uh, both temperature and pressure. But when the volume is reduced, both of them go up by a lot. This is expected because volume, as it decreases, and remember it needs to stay constant, pressure times volume divided by temperature. Therefore, pressure and temperature have to go up in order to account for the reduced volume. Uh, but as you can see here, pressure stays roughly constant along the way, but temperature starts to decrease rapidly. This is because the pressure is in a way fixed inside this range. It cannot it cannot interact as fast or as efficiently with the outside world, with the ambient pressure. And the temperature is the opposite. It is not isolated from the outside world because the syringe touches the air outside, so therefore it starts to cool down, trying to get back to the ambient temperature. And when the volume starts to rise up, we can see the opposite effect. Now both of them have to go down, but they go down way below the original ambient temperatures. Temperature goes way below the ambient temperature, but pressure doesn't. This is because as it starts to go upwards, this range, temperature has to start to decrease in order to account for the change. And as the pressure cannot be mm, as the pressure has stayed roughly constant, but temperature has already gone down. This downwards, this already downward temperature has to go even more lower than when it started because it has lost some of the energy to the air outside. So therefore, it goes way below the original temperature. But pressure doesn't because, as I said, it stays roughly constant. So therefore, it didn't lost a lot of energy. Therefore, it does not have to go below the original one. But as you can see, pressure stays roughly the same as before, but temperature again goes back upwards to the ambient temperature. It's really important to see that pressure does not go to the exact same point it was before at the start of the experiment. This is because the volume doesn't also go to the same exact point. If you see the video of the experiment, you can see that the final volume is not the same as the one that it started. It doesn't go all the way up. This is due to, again, the loss of energy of both temperature and pressure. Okay, now for the second part of the experiment. Here are the results we got by testing the way I said before, how we're going to test for the second part. Here are the values of the volumes, pressures, and temperatures at different points. Now what we're going to do is get temperature divided by pressure. In this case, because it's kilopascals, the unit is millikelvin divided by pascals. We also have the uncertainty. The uncertainty is calculated using the formula for the uncertainty of a division. As you can see here, the uncertainty of x over y, in this case x is temperature and y is pressure, is equal to the square root of the change in x by y squared plus minus the change in y times x over y squared, all of that squared. This is because of how their derivatives are calculated. So accounting for both of these, we can get the uncertainty for this, and the uncertainty of the volume is just the half at the tick mark of the syringe, which is 0.05 cubic centimeters. Now we're going to graph volume versus temperature divided by pressure, and this will get us the next graph. As you can see, it very closely follows a linear path. This is because if we see here the formula of pressure times volume equals the number of moles times R times temperature, and we divide pressure on both sides, we get that volume is equal to N times R times temperature divided by pressure. And this is what our graph is. Y is volume and X is temperature divided by pressure. Therefore, the slope has to be N times R. And as we said before, this is a constant, so therefore it uh, is a linear best fit line. So the data does follow the ideal gas law, but not exactly, because if this were exactly, there will be no discrepancy on the y-axis. There wouldn't be a y-intercept. But as you can see here, represented by the letter B, there is around -2 cubic centimeters. This is because we also haven't accounted here for the original volume of the syringe as we saw in the last part. And this is the discrepancy of around 2.5 cubic centimeters. And as you remember, on the previous experiment, we got that volume zero will be 2.3 cubic centimeters. So this second experiment tells us we were roughly correct, just by around zero point 0.2 errors in the cubic centimeters, which, as you can see here, it's also counted in the uncertainty. So therefore, this is another confirmation that volume zero was correct on the previous experiment. But most importantly, we can get from the slope the value of the number of moles times R, which will be around 21.21 cubic centimeters times kilopascals by Kelvin. Now, R is equal to 8.31 times cubic meters times pascals divided by Kelvin times moles. So when we try to calculate the value of the number of moles, we need to change the units to this. Cubic centimeter is actually a million cubic centimeters makes a cubic meter. So a cubic centimeter is 10 times to the minus 6 cubic meters. We also, because it is in kilopascals, the 10 times to the minus 6 multiplied by the 10 times to the 3. So at the end, it's the same units as R, but times 10 to the minus 3, or 1,000 times smaller. Accounting for both of these on the uncertainty and the value, and then divided them by R, we get that the number of moles is actually 2.55 millimoles, or a thousandth of a mole. And this is expected because it is a very small volume, and for gases, a mole uh, it needs to be small as well. So 2.55 millimoles is roughly what we expected around the same power. So therefore, here we can see how the Delgas law can actually tell us how much moles are in this gas. Thank you for watching.